School of Management Studies IGNOU presents an audiobook on the course MMPC 005 Quantitative Analysis for Managerial Applications for MBA program. Block 2 Probability and Probability Distributors. Unit 5 Basic Concepts of Probability.
Basic concepts of probability. After completing this unit, you should be able to appreciate the relevance of probability theory in decision making, understand the different approaches to probability, calculate probabilities in different situations, and revise probability estimate if added information is available. Introduction. Uncertainty is a part and parcel of human life. Whether stock market prices, product quality are but some of the areas where commenting on the future with certainty becomes impossible. Decision making in such areas is facilitated through formal and precise expressions for the uncertainties involved. Study of rainfall spelled out in a form amenable for analysis may render the decision on water management easy. Intuitively, we say that if there is a high chance of a large quantity of rainfall in the coming year, we may decide to use more water of rainfall for power generation and irrigation this year. We may also take some steps regarding flood control. However, in order to know how much water to release for different purposes, we need to quantify the chances of different quantities of rainfall in the coming year. Similarly, formal and precise expressions of stock market prices and product quality uncertainties may go a long way to help analyze and facilitate decision on portfolio and sales planning respectively. Probability theory provides us with the ways and means to attain the formal and precise expressions for uncertainties involved in different situations. The objective of this unit is to introduce you to the theory of probability. Accordingly, the basic concepts are first presented, followed by the different approaches to probability measurement that have evolved over time. Finally, in the last two sections, certain important results in quantifying uncertainty which have emerged as a sequel to the theoretical developments in the field are presented. Basic concepts, experiment, sample space, and event. Probability in common parlance connotes the chance of occurrence of an event or happening. In order that we are able to measure it, a more formal definition is required. This is achieved through the study of certain basic concepts in probability theory, like experiment, sample space, and event. In this section, we explore these concepts. Experiment. The term experiment is used in probability theory in a much broader sense than in physics or chemistry. Any action, whether it is the tossing of a coin or measurement of a product's dimension to a certain quality or the launching of a new product in the market, constitute an experiment in the probability theory terminology. These experiments have three things in common. They are: number 1, there are two or more outcomes of each experiment. Number 2, it is possible to specify the outcomes in advance. And number 3, there is uncertainty about the outcomes. For example, a coin tossing may result in two outcomes, in head or tail, which we know in advance, and we are not sure whether a head or a tail will come up when we toss the coin. Similarly, the product we are measuring may turn out to be undersize or right size or oversize, and we are not certain which way it will be when we measure it. Also, launching a new product involves uncertain outcome of meeting with a success or a failure in the market. Sample space. The set of all possible outcomes of an experiment is defined as the sample space. Each outcome is thus visualized as a sample point in the sample space. Thus, the set, head or tail, defines the sample space of a coin tossing experiment. Similarly, success or failure defines the sample space for the launching experiment. You may note here that given any experiment, the sample space is fully determined by listing down all the possible outcomes of the experiment. Event. An event in probability theory constitutes one or more possible outcomes of an experiment. Thus, an event can be defined as a subset of the sample space. Unlike the common usage of the term, where an event refers to a particular happening or incident, here we use an event to refer to a single outcome or combination of outcomes. Suppose as a result of a market study experiment of a product, we find that the demand for the product for the next month is uncertain and may take values from 100, 101, 102 till 150. We can obtain different events like the event that demand is exactly 100, the event that demand lies between 101 to 120, and the event that demand is 101 or 102. In the first case, out of the 51 sample points that constitute the sample space, only one sample point or outcome defines the event, whereas the number of outcomes used in the second and third case are 20 and 2 respectively. With this background on these concepts, we are now in a position to formalize the definition of probability of an event. In the next section, we will understand the different approaches to probability that have been developed and present the axioms for the definition of probability. Different approaches to probability theory. Three different approaches to probability have evolved mainly to cater to three different types of situations under which probability measures are normally sought. In this section, we first explore the approaches through examples of distinct types of experiments. The axioms that are common to these approaches are then presented and the concept of probability is defined using the axioms. Consider the situations marked by three distinct types of experiments. The events that we are interested in within these experiments are also mentioned here. Situation 1. Experiment is drawing a number from among 9 numbers, say 1 to 9. Event is on any draw, number 4 occurs. Situation 2. Experiment is administering a particular drug. Event is the drug puts a person to sleep in 10 minutes. Situation 3. Experiment is commissioning a solar power plant. Event is the plant turns out to be a successful venture. The first situation is characterized by the fact that on any draw, each of the 9 numbers has got equal changes of occurrence if the experiment is conducted with fairness. Thus, in any draw, any one of the numbers may turn up and the changes of occurrence of each is equal. This type of a situation marked by the presence of equally likely customers gave rise to the classical approach of probability theory. In the classical approach, probability of an event is defined as the number of outcomes favorable to the event over total number of outcomes. Thus, if we denote the event that a 4 comes out in a draw as A and the probability of the event as P in bracket A, then we can see that the total number of outcomes in a draw of numbers 1 to 9 is 9, as any one of the numbers may occur. The number 4 occurs only once in these 9 outcomes. Thus, P in bracket A equals to 1 by 9. Now let's look at the second situation. If we try to apply this definition of probability in the second experiment, we find that we cannot say that the drug will be equally active for all persons. Moreover, we do not know as to how many persons have been tested. This implies that we should have the past date on people who were administered the drug and the number that fell asleep in 10 minutes. In the absence of past data, we have to undertake an experiment where we administer the drug on a group of people to check its effect. We are assuming here that experimentation is safe, that is, the drug does not have any side effects. The relative frequency approach is used to compute probability in such cases. As per this approach, the probability of occurrence of an event is given by the ratio of the number of times the event occurs to the total numbers of trials. Denoting the event by B and the probability of the event by P in brackets B, we can write P in brackets B equals to number of persons who fell asleep in 10 minutes over total number of persons who were given the drug. It was recognized in this approach that in order to take such a measure, we should have it tested for a large number of people. In other words, the total number of trials in the experiment should be very large. The third situation seems apparently similar to the second one. You may be tempted here to apply the relative frequency approach, denoting by C the event that the venture is a success and P in brackets C the probability of success. You may calculate P in brackets C as number of successful ventures over total number of such ventures undertaken. That is, the relative frequency of successes will be a measure of the probability. However, the calculation here presupposes that either number 1, it is possible to do an experiment with such ventures, or number 2, that past data on such ventures will be available. In practice, a solar power plant being a relatively new development involving the latest technology, past experiences are not available. Experimentation is also ruled out because of high cost and time involved, unlike the drug testing situation. In such cases, the only way out is the subjective approach to probability. In this approach, we try to assess the probability from our own experiences. We may bring in any information to assess this. In the situation cited, we may perhaps look into the performance of the commissioning authority in other new and related technologies. You may note here that since the assessment is a purely subjective one, it will vary from person to person. Let us assume that we are interested in finding out the chances of getting ahead in the toss of a coin. By now, you would have come up with the answer by the classical approach using the argument that there are two outcomes, heads and tails, which are equally likely. Hence, given that a head can occur only once, the probability is 1 by 2. Now consider the alternative line of argument where the probability can be estimated using the relative frequency approach. If we toss the coin for a sufficiently large number of times and note down the number of times the head occurs, the proportion of times that a head occurs will give us the required probability. Thus, given a definition of the approaches, we find both the arguments to be valid. This brings out in a way the commonality between the relative frequency and the classical approach. The difference, however, is that the probability computed by using the relative frequency approach will be tending to be 1 by 2 with a large number of trials. Moreover, an experiment is necessary in this case. In comparison, in the classical approach, we know a priori that the changes are 1 by 2 based on our assumption of equally likely outcomes. As already noted, the different approaches have evolved to cater to different kinds of situations. To highlight the commonality of the classical approach and the relative frequency approach vis-a-vis the third approach, the first two are sometimes referred to as the objectivist measures in contrast to the subjectivist measure of the third approach. All these approaches, however, share the same basic axioms. These axioms are fundamental to probability theory and provide us with unified approach to probability. The axioms are: number 1, the probability of an event A written as P in brackets A must be a number between 0 and 1, both values inclusive. Thus, 0 is less than equal to P in brackets A, which is less than equal to 1. Number 2. The probability of occurrence of one of the other of all possible events is equal to 1. As S denotes the sample space or the set of all possible events, we write P in brackets S equals to 1. Thus, in tossing a coin once, P, that is a head or a tail, is equal to 1. Number 3. If two events are such that occurrence of one implies that the other cannot occur, then the probability that either one or the other will occur is equal to the sum of their individual probabilities. Thus, in a coin tossing situation, the occurrence of a head rules out possibility of occurrence of tail. These events are called mutually exclusive events. In such cases, then, if A and B are the two events respectively, then P in brackets A or B equals to P in bracket A plus P in bracket B. That is P in bracket head plus P in bracket tail. You may note here that these being axioms, they cannot be proved. It follows from the last two axioms that if two mutually exclusive events form the sample space of the experiment, then P in bracket A or B equals to P in bracket A plus P in bracket B, which is equal to 1. Thus, P in bracket head plus P in bracket tail equals to 1. If two or more events together define the total sample space, the events are said to be collectively exhaustive. Given these axioms, we may not define probability as a function which assigns probability value P to each sample point of an experiment abiding by these axioms. Thus, the axioms themselves define probability. We are not in a position to look into the process of calculating probabilities for more complex situations. In the next section, we attempt this through a study of the probability theorems. Calculating probabilities in complex situations. In the last section, we have seen how to compute probabilities in certain situations. The nature of the events were relatively simple, so that direct application of the definition of probability could be used for computation. Quite often, we are interested in the probability of occurrence of more complex events. Consider, for example, that you want to find the probability that an ace or a spade will occur in a draw from a deck of 52 cards. You may be interested in the occurrence of this event because you have betted on the same. Similarly, on examining couples with two children, if one child is known as a boy, you may be interested in the probability of the event of both the children being boys. These two situations, we find, are not as simple as discussed earlier in the section. As a sequel to the theoretical development in the field of probability, certain results are available which help us in computing probabilities in such situations. Revising probability estimate. As we have already noted in the introduction, the basic objective behind calculating probabilities is to help us in making decisions. Quite often, whether it is in our personal life or our work life, decision making is an ongoing process. Consider, for example, a seller of winter garments. You are interested in the demand of the product. To help you in deciding on the amount you should stock for the winter, you have computed the probability of selling different quantities and have noted that the change of selling a large quantity is very high. Accordingly, you have taken the decision to stock a large quantity of the product. Suppose, when finally the winter comes and the season ends, you discover that you are left with a large quantity of stock. Assuming that you are in this business, you feel that the earlier probability calculation should be updated given the new experience to help you decide on the stock for the next winter. Similarly, situations exist where we are interested in an event on an ongoing basis. Every time some new information is available, we do revise our odds mentally. This revision of probability with added information is formalized in probability theory in terms of a theorem known as Bayes' theorem. Bayes' theorem. It states that if A and B are two mutually exclusive and collectively exhaustive events, and C is another event defined in the context of the same experiment, then given the values of P in bracket A, P in bracket B, and P in bracket C by A and P in bracket C by B, the conditional probability is P in bracket A by C equals to P in bracket C by A into P in bracket A over P in bracket C by A into P in bracket A plus P in bracket C by B into P in bracket A, and P in bracket B by C equals to P in bracket C by B into P in bracket B divided by P in bracket C by B into P in bracket B plus P in bracket C by A into P in bracket A. Let's now discuss an application of this theorem. Consider the case of a manufacturer who is using a particular machine for producing a product. From earlier data, he has estimated that the chances of the machine being set correctly or incorrectly are 0.6 and 0.4 respectively. Thus, we have two mutually exclusive and collectively exhaustive events. So the A is setup is correct and B will be the setup is incorrect. With P in brackets A equals to 0.6 and P in brackets B equals to 0.4, you can check P in bracket A plus P in bracket B equals to 1. And this follows from definition mutually exclusive and collectively exhaustive events. From the past data, the manufacturer has estimated that when a machine is set correctly, it produces 10% defectives, otherwise it produces 60% defectives. Now suppose before going for the batch production, one unit has been produced, inspected and found to be defective. The manufacturer wants to find out in what way this new information affects the probabilities of the events A and B. In other words, given added information, what is the probability of the event A and B? Or we can say, given added information, what is the probability that the setup is correct? So here AC is A defective occurs with setup correct and BC is A defective occurs with setup incorrect. So now we have this first equation, which is P in bracket C equals to P in bracket AC plus P in brackets BC. We also have the data on conditional probabilities, where P or defective or setup correct equals to P in bracket C by A equals to 0.1 and P or defective or setup incorrect equals to P in bracket C by B, which is equal to 0.6. So from the result 3 of the last section, we know that P in brackets AC equals to P in bracket C by A into P in bracket A and P in bracket BC equals to P in bracket C by B into P in brackets B. Therefore, first equation can be written as P in bracket C equals to P in bracket C by A into P in bracket A plus P in bracket C by B into P in bracket B. Now we are interested in finding the probability that the setup was correct given that a defective piece has come out, that is P in bracket A by C. So again from the result 3, we derive that P in bracket A by C equals to P in bracket AC over P in bracket C, which is again equal to P in bracket C by A into P in bracket A divided by P in bracket C by A into P in bracket A plus P in bracket C by B into P in bracket B. Hence, the proof of the Bayes theorem goes as P in bracket A by C equals to, here we will put the values 0.10 into 0.6 divided by 0.1 into 0.6 plus 0.6 into 0.4, which is equal to 0.06 divided by 0.06 plus 0.24, which is equal to 0.2. Thus, with the new information, we have revised the probability estimate of a correct setup. As the new piece was defective, this has reduced the probability of correct setup. We can consider a further variation in this situation. Suppose, instead of basing his calculation on a single piece, the manufacturer produced 2 pieces before going in for batch production. If he found both the pieces defective, what is the probability that the current setup is correct? Now, the event C is defined as both pieces being defective. Hence, P into in bracket C by A denotes the probability that given the setup was correct, both pieces have turned out to be defective. The change of one defective with a correct setup is 10%. Therefore, P in bracket C by A equals to 0.1 into 0.1, which is equal to 0.01. Similarly, P in bracket C by B equals to 0.6 into 0.6, which is equal to 0.36. So here we will apply the theorem directly, and the result that we get is P in bracket A by C equals to P in bracket C by A into P in bracket A divided by P in bracket C by A into P in bracket A plus P in bracket C by B into P in bracket B, which is equal to 0.01 into 0.6 divided by 0.01 into 0.6 plus 0.36 into 0.4, and the answer is 0.04. This formula demonstrates the method of using added information to revise the probability estimates. With this section, we are in a position to calculate probabilities under different situations. However, we have not demonstrated explicitly as to how exactly this probability information can be used for decision making. Before we do this, certain other concepts and standard representations in probability theory need to be discussed, and we will take up these issues in the subsequent units. Now let's summarize the unit. Probability in common parlance means the change of occurrence of an event. The need to develop a formal and precise expression for uncertainty in decision making has led to different approaches to probability measurement. These approaches, namely the classical, the relative frequency, and the subjectivist approach, arose mainly to cater to different types of situations where we face uncertainties. The approaches, however, share the same basic axiom. In this unit, we have used these axioms to define probability formally, and the definition has been used to calculate probabilities of different types of events. As the events of interest to us become more complex, the computation of probability through definition turns out to be tedious. Certain results in probability theory which are helpful in this context have been presented. The need to revise the odds in the light of new information is felt in many situations. In the final section of this unit, we have shown the method to revise the probability estimate as added information on the outcome of the experiment becomes available.
We were listening to the audiobook by the School of Management Studies IGNOU for MBA program, course code Mmpc 005, Quantitative Analysis for Managerial Applications. Course Coordinator, Professor Anurag Saxena, School of Management Studies IGNOU. Voiceover by Harpreet Kaur. Edited by Ashok Sharma. Program assisted by Tarannum Jahan and Jagbandhu Jana. Program produced by Dr. Manoj Kumar Singh. This program was brought to you by Electronic Media Production Center of Indira Gandhi National Open University.